So today's lesson, we're going to go through your internal and how you can get a achieved, merit, and for you guys, all excellences in this upcoming assessment. So when you're looking at your merit and excellent level, you have to discuss systematic and random errors and ways you can improve it during your experiment. So examples of systematic errors can be checking for zero errors. For example, have you got a ruler with you and is it 5 centimeters sawn off from the end? That would be a systematic error. Did you re-zero the scales when you're measuring the mass of something? Or did you use an ammeter and was it non-zeroed? That's an example of a systematic error. You can avoid parallax errors by having your eye level with the ruler and seeing the quantity that's being measured and perpendicular to the scale on the ruler. That's another example of a systematic error which you can remove. And when you're checking the measuring instrument, be it a ruler or a balance, by using another for the same measurement, especially when you're using Newton meters. Okay, so if you have using one balance, then you use another balance to check that your first balance is precise and accurate. Remember also, if you're doing, say, oscillations of a spring, to count properly. For oscillations, lots of students count from 1 rather than 0. Also, lots of students time half the oscillations rather than a full oscillation, which is the period which you're supposed to be calculating. And remember that repeating readings does not reduce systematic error. It reduces random error. If you have a systematic error, that's going to be in every reading. So even if you do more than one reading, it's still going to be there. So random errors. So repeating and averaging improves precision by reducing these random errors. So examples of random errors, for example, could be wind coming through the classroom, through air conditioning, which is putting off your pendulum. So in terms of the pendulum, timing multiple oscillations improves precision, and also any inaccuracy in the measurement is divided by the number of oscillations timed. Okay, so if you've got one random error out of 100 values, then if you do 100 values, that one random error is divided by 100, reducing it. Another example, if you're using voltmeters or ammeters or measuring something with electricity, if you're using a digital multimeter to measure a quantity, either voltage, resistance, or current, you select the scale which gives you the greatest number of significant figures. That helps reduce random error because it reduces the sensitivity of the device, and reducing sensitivity means that it's not as sensitive to the random errors associated with the experiment. So also around merit and excellence, rounding and significant figures will be critical. So for a single measurement, the number of significant figures is determined by the smallest scale division. So for example, if you're measuring with a ruler and it's marked in millimeters, the smallest length could be to one significant figure, for example 8 millimeters, but the longer length for say longer pendulum length could be to 3 significant figures like 268 millimeters. When you're doing the pendulum experiments, single timing should be to 1 decimal place. For example, 2.38 seconds should be rounded to 2.4 seconds for those, say, over 10 oscillations. And sensible rounding may also be needed. So for the height of a bouncing ball, you round it to the nearest centimeter, even if you're using a millimeter scale. Again, continuing on with significant figures and repeated readings, which is required for merit and excellence level. If you repeat a measurement several times and find the average, then the answer should be the same number of significant figures as your measurements. So for example, if you have measurements of 67, 62, 68 and 65 centimeters for an average bounce height, and you take an average, I don't want to see 65.333 because the accuracy of your readings is determined by the individual readings. So because you have two significant figures as your individual readings, then your average should also be in two significant figures. You should round it to 65. And for the oscillations of a period of a string and a pendulum, for timing multiple events, say 10 oscillations, you time to the nearest 0.1 seconds, then your answer should be to the nearest 0.1 seconds because 0.1 divided by 10 gives you 0.1 seconds. Okay, so an example here, if it takes 10 oscillations of this pendulum 14 seconds to happen, therefore one oscillation should take 1.47 seconds. So an important aspect of this internal is the use of graphs. I'm going to focus on linear graphs first, which will be kind of going over what you did in level 1, and then going to push it on to non-linear graphs, which is actually the crux of this internal. Right, so what's the point of drawing a graph? Okay, sometimes it's easy to see a pattern of results. So here we have time in seconds and size in meters. You can clearly see as time increases, then the size increases as well, double the time. However, sometimes it's not that easy. So here we have some data here of time in degrees Celsius, and it's a bit more difficult to see the relationship between time and the temperature. This is where graphing comes in. So graphs help us see mathematical relationships and patterns. And in physics, patterns are important. So is there any pattern in the results? So look at that raw information or raw data, and can you see a pattern? Probably not. The numbers are kind of all jumbled about. It's very difficult to see a relationship, but it's hard to see a pattern. But if you plot it, you can clearly see a linear relationship. Okay? Time is directly proportional to temperature if we plot that graph. And we also draw a line of best fit. So by plotting a graph, you can clearly see a relationship between temperature and time, which could be unclear from the tabulated results that you've generated. So one of the first aspects of drawing a graph is drawing the right axes for your graph. This can be quite tricky and will always depend on the results you have to plot. 3 points to try and consider when working out the size of a graph are: try and make the scales go up in easy numbers, so multiples of 1s or 2s or 5s or 10s or 20s. There we go there, so that's going up in 5s, and the minutes are going up in 1s. Right. And you also have to draw a line of best fit. Now, one of the most common mistakes I see in marking these internals is joining the dots up one by one. You're no longer in year 7, you're doing year 12 physics, so it means that joining dots is no longer acceptable. You have to use a line of best fit. So here we have some data that has been plotted on the graph. And as you can see, doing it this way, you join the dots. This gives a very uneven line, and you can't really see any kind of linear or any kind of pattern in that relationship. However, by trying to draw a smooth line near to as many points as possible, you can see a clear linear relationship. Okay, so more about this line of best fit. So when drawing a line of best fit, it's important to try and get some of the numbers or points above and below the line. And so each of the graphs below is the same, right? So in that example here, the line is too low, the line is too high, whereas just like in Goldilocks, the line's just right in that third example. Okay, so in the first example, the line was too low, it didn't encapsulate enough of the data points. In the second example, the line was too low, didn't encapsulate enough of the data points, whereas the line in the third example is just right because it encapsulates a majority of the data points within a range. So continuing on with line of best fit, as you can see, it's quite important. Not all lines of best fit can go through the origin 0, 0 and 0. By and large, for this internal, it's more than likely they will, but you have to be careful. So here's an example here. So this line goes through the origin, but it's not right, whereas this one does, and it doesn't go through the origin. Okay, so which one matches the information or the data points, the left or the right? Quite clearly, it's the right. Okay, so now we're going to spot the best fit line. So in each of the cases below, try and imagine where the best fit line will go before it actually appears. So here's some data points. Pause the video now and try and work out where the line of best fit goes. Okay, so welcome back. So you should note that the line of best fit goes through the points as such. Best fit lines can go down as well as up. So here is an example of a non-linear relationship, which we're going to be moving on to. And you can clearly see that the line of best fit in this example is not going to be a straight line. It's going to be a gentle, smooth curve, because best fit lines can also be curved. And finally, with these data point here, best fit lines can also change shape. So now it's going to the point of describing the pattern. Now, describing the pattern is critical for the achieved merit and excellence component of this internal. You need to be able to describe the pattern in all three cases. So if there is a pattern, then it's important we try and describe it. So here we have two variables, A, which is the dependent variable, and B, which is the independent variable. So we're changing B and getting an effect in A. So as A increases, B increases. Now this is something you may have seen in your internal last year for level 1. As the mass of the weight that the mass increased, then the extension increased. As weight increased, weight force increased, then B increased. That was last year. It's a linear relationship. Okay, this is an example here is as A decreases, B increases. Okay, so for example, A could be the amount of work you're doing in class, and B could be the pressure you're feeling from your parents. So as A, the amount of work you do decreases, then the amount of pressure from your parents to do work increases. And finally, as A increases, B increases up to point X, and after this point B increases, A does not change. Quite common in chemistry where you have rates of reaction. So, are all best fit lines as good as each other? Well, different sets of results may show different patterns, but some sets of results may look better than others. It's important to note though, in your internal, you deal with the results or the data points that you get. Okay, you can't fudge the results to suit what you think you will get, because it's kind of putting the cart before the horse. You get the results you get, and it has to follow a certain pattern, so be it. Okay, so here's two examples. So we have on the left some data points, and on the right some other data points. So is any data better than the other? Well, you can get a nice straight line through all the data points in the one on the left, whereas it's kind of a mixture. In the second one on the right, that might be due to systematic and random errors, something you can discuss and justify in your internal write-up, which will be the merit excellence aspect of the internal. In both cases, the line of best fit is exactly the same. Okay, just the data points tend to be more spread out in the case on the right hand side. So if all the points are close in the line, then we say that the results are reliable. Okay. The results of both graphs show the same pattern, but the results are considered more reliable in the left-hand case than in the right-hand case. And this could be due to systematic errors or random errors, which you need to discuss if you get this kind of data. Okay, so just a checklist for linear graphs. It's critical you give your graph a title. It's critical you choose a sensible scale for both axes and go up in sensible increments and equal increments. Try and draw your graph so it fits the entire graph paper. I don't want to see postage stamps. 4, label your axes. It's important. I just don't want to have random numbers. It's like, what does this number mean? I've got no idea. Important also with your axes that not only do you label them with, say, temperature or time, you put the units on both axes. So if you have time versus temperature, then you've got degrees Celsius for temperature and time is in seconds. Okay, plot the points correctly and you mark them with a cross. Okay, and then you draw a smooth best fit line through the points. This is often called the trend line, and it shows a general trend, but you do not have to join up all the points. You need to just do a line of best fit. This is for linear relationships as much as the smooth curves and non-linear relationships. So it's important too that you recognize any outliers, ones that are way off the general trend. You circle these and you label them saying this is an outlier, and you point out in your discussion why this is an outlier. So you may have non-zeroed for a particular value, or you may have had a parallax error, or a wind gust may have come through the classroom and made the spring swing, for instance. And finally, draw the line clearly and finally. So that's linear graphs. So non-linear graphs. So in this internal, if you produce a non-linear graph from the data you get from your experiment, you're on to an achieved kind of framework. If you then convert the nonlinear graph into a linear graph, then that is in your merit and excellence. So you should have two graphs if you want to get merit and excellence. So the graph shapes. So if you plot your data from the experiments you do in the internal, if you get a curved line up, it means that y is proportional to x squared. This is known as a squared relationship. So y is proportional to the square of x. Okay, it's another way of writing that, and I'm going to write it there. Y is proportional to x squared. Okay. Whereas if you get this kind of asymptotic relationship there, y is inversely proportional. So y is proportional to 1 over x. And if you get a tighter line here more towards the origin, then y is going to be proportional to 1 over x squared. Now it's important here that we note that although we're using y and x, in the experiment you're not going to be using y and you're not going to be using x. You might be using power for, say, the y value, and current will be the x value. You need to be able to use these values and replacing x and y when you're writing up the internal. Okay, moving along. So here's an example of y is proportional to x squared. So what you do if you have this relationship in your internal is you add a third column to your experimental results with x squared or I squared, whatever value you've got for x. Now plot y versus x squared. Okay, not y versus x, y versus x squared. So if you see a relationship like this in your non-linear graph, then you're looking at y versus x squared for your second graph. Okay, if your guess was right, you should now see a straight line when you plot y versus x squared. Find the gradient of the line m, and the relationship will be y equals mx squared. Or another way of putting it is the dependent variable equals the gradient times the independent variable squared. It's important to note that you're going to be using, instead of using x and y, you'll be replacing y with whatever the dependent variable is, and replacing x with whatever the independent variable is. Okay, you've got y equals is inversely proportional to x. Okay, again, you're adding a third table, this time with 1 over x. If you get a nonlinear graph of like this, okay, and now you plot y versus this time 1 over x. If your guess was right, you again should see a straight line. You find the gradient, and the relationship is y equals m times 1 over x, or y equals m divided by x. I recommend focusing on that there. Or, in other words, the dependent variable equals the gradient divided by the independent variable. An example there would be power equals the gradient divided by v. Next relationship is y is inversely proportional to x squared. Again, you're adding a third column, this time with 1 over x squared. If you plot y versus 1 over x squared, again, you'll find a straight line if this is the correct relationship, and it should look very much like this, called a nonlinear graph. Okay, and then y equals m divided by x squared, or the dependent variable equals the gradient divided by the independent variable squared. For example, force equals 34 divided by d squared. Okay, this third column discussion point is when you're trying to aim for merit and excellence, which you all should be. Okay, so don't forget we use x and y as only general examples. In your internal, the variables will use different letters. So for example, if they're going to do an experiment with pressure and volume, instead of using y, you'll use pressure, and instead of using x, you'll use volume. Do not talk about x and y in your internal, okay? I don't want to see that. You should be discussing the independent and dependent variables that you're actually using in your experiment, which you're doing for your internal. Okay, so another point is the units. So all graphs axes need a label and a unit. So for the non-linear graphs you'll be generating to get achieved, it's quite simple to work out what the units are. They are going to be the units of the variables that you're measuring. But when you're transferring into linearizing the nonlinear relationship, then you have to be careful with the units that you're going to be putting on your label. So if the units of x are kilograms in your plot of the nonlinear plot of y versus x, then the units of x squared are going to be kilograms squared. If the units of x are kilograms, then the units of 1 over x are going to be kilograms to the minus 1, which you're going to then use as your units for your x-axes in your linear graph. And if the units of x are kilograms, then the units of 1 over x squared are going to be kilograms to the minus 2. It is critical that you put the right units in the table and on the graph when you are doing your internal and plotting your linear graph from the nonlinear relationship that you've just plotted. This is the second graph. Otherwise, you cannot get anything more than an achieved. And as we know, we're all aiming for excellence, so you should be placing the correct units in your linear graph, your second linear graph, which you require to do to get merit and excellence. Okay, so a final point for excellence is you have to get the correct units for the gradients that you've calculated from your second linear graph. And this can be a bit confusing. The general rule is that the gradient unit is going to be y unit times the x unit to the minus 1. And examples are outlined here, which I'm going to go through in detail. Okay, so if we do a plot of meters against seconds in a straight line, then the gradient will be, the units will be meters, which is the y unit, times the x unit, which is in seconds to the minus 1, which is meters per second, which makes sense because distance divided by time is velocity. So gradient would be velocity. If we have joules this time against meters squared area, then the gradient will be the y unit times the x unit to the minus 2 this time, because meters squared times minus 1 is minus 2, so it'll be joules per meter squared. And the final one would be kilograms to the minus 1, which will be meters, which is your y, times kilograms, which is your x to the minus 1. Minus 1 times minus 1 is 1. So it'll be meters, the gradient will be meters times kilograms. So for nonlinear graphs, these are the rules. Plot as normal and draw a freehand best fit curve. Then look at the shape of the graph and guess the form of the relationship between the two variables. Add a third table column with the independent variable changed according to the guessed relationship, so be it 1 over x, x squared, square root of x, 1 over x squared. Then you plot a second graph, which is going to be your merit and excellence. And if your guess was right, your new graph should be a straight line. So hopefully that's helped you and kind of cleared up some ideas of how this internal will run. And I look forward to you all succeeding.